So only one thing is left that remains to be proven about the construction of the quotient group. So far we've proven, so as a reminder, so far we've proven, so given group G, normal subgroup N, we have G mod N, which is a set of left cosets of N in particular. And so this is a set of left cosets. So far we've had that we have a law of composition. We've shown that, and then we've proved this lemma, that if G is surjects onto Y, so if there's a surjective map from G to Y, which has so we better call it phi, we better call it something. So, well, actually I was calling it P earlier, P for projection. So let's call it P, P, which has P of A, B equals P of A, P of B, where Y might not be a group. Y is a set with a law of composition. And then the conclusion of the lemma was that Y is a group, and that P is a homomorphism. So now we can apply this lemma to the map from P from G to G mod N, and that will, so that map, right, we take an element, we send it to its left coset, and that map is surjective because the cosets partition G, and so as a result we apply this lemma, the conclusion, so G mod N is a group. So that's nice. And we also got that P is a morphism. Right? Reminder, homomorphism, morphism, same thing. So the last thing we need to prove, so the last thing we need to show is that the kernel of P is exactly N. So let's think about what the kernel is. So what's the kernel of P? That's the set of things that, set of A in G such that P of A equals 1. And so if we remember what 1 is in G, right, this is a set of A in G such that P of A, well, this is going to be the coset 1 times N, because that's the identity element. That's because the identity element is going to be P of 1, right? Homomorphisms always follow the rule that they map 1 to 1. That was proved in an earlier video, and the thing that 1 maps to is precisely the coset of 1, which is, of course, just the subgroup N. So the things that land in the subgroup, the coset of 1, which is equal to just the subgroup of N. So we know that P of A equals n, or an equals 1n, which is just n, of course. So it's the set of things where an equals n. So this is the same thing as saying that, and so what we need to see now is that this is the same thing as saying that A is inside of this normal subgroup N. Why is that true? Well, okay, first of all, you know, we have that, so if an, so if A is in N, that means that an equals N, and that's by the closure. That's by the closure of the subgroup N. So that's one direction of what we need to show. And then the other direction is, right, so that will show that if an is in N, then A is in the kernel, because A has this property, which we figured out was what the set of things of the kernel were. So this shows that N is contained in the kernel of P. Okay, and now what does it mean for an to be equal to n? Right, that's the set of an for little n and n is equal to the subgroup n. So in particular, a times n equals n prime. So I guess maybe I should write it out like this. Subgroup of, I should use the name n prime in n. So okay, what did I do with this step? What I did was I just wrote out what the definitions of these sets here are. So this is just sort of trivially writing out, oh, the elements of the set n are in fact those elements that are in the set n. Okay, that's fine. And then this is just writing out what the definition of the coset is, / the product set notation. And so what I can write is I can write an equation like this for some, I don't know which one, but for some n and n prime. And what that's going to tell me, if I move this over so I have some space, is I can multiply, so that means that A is going to be equal to n prime times n inverse. And this is definitely in the subgroup N, right? Closure, inverses, all good there. And so that means that A is in N, which is what we needed to show. So now this is a if and only if, and this is not just an inclusion, that's an equals.